Now let's have a look at graphing motion. First up's position time graphs. If we wanted to show the position of the puck in 2 dimensions, here I've labelled the x dimension and the y dimension, that would be very difficult. So in this course what we're going to be doing is locating the puck just in 1 dimension. So we'll talk about position in terms of 1D. So here I've labelled the centre of my ice hockey rink as the origin, the 0 metre mark, and then we see a positive direction, so positive 15 and then positive 30 metres, whereas the other direction I'm using my directed numbers to indicate left, negative 15 and negative 30 metres. Let's have a look at a possible position time graph. Here we see position on the y-axis and time on the x-axis, and we see the motion of the puck is described over an interval of 8 seconds. The position time graph I've shown you here describes this scenario where Ada hits an ice puck to Ben, and then Ben hits the ice puck back. So the first question I'd like to ask here is, well, where are the positions of Ada and Ben? Well, Ada hits the ice puck first, so the puck starts at a position of plus 20 metres, and then we see the position of the puck changing. So this must be where Ada hits the puck, so Ada must be located plus 20 metres, so in this X position here. Then Ben, if we look at our graph, the puck stops at 4 seconds. This must be where Ben is positioned at minus 10 metres. So very importantly here, from a position time graph, we can read directly from the graph the position of the puck at any time. Now over the 8 seconds of motion, let's consider the displacement and the distance travelled by the puck. So over the 8 seconds, the displacement is equal to the change in position. So it started off at the plus 20 metre position, and it finished at the plus 20 metre position. So the displacement of the puck here is 0 metres. Notice it doesn't matter what happened to the puck in that time interval, just the position that it started and finished in that time interval. We can also calculate the distance travelled by the puck over the 8 seconds. Here we have to look at individual segments of our graph. So from 1 second to 4 seconds, the puck travels from plus 20 to minus 10. That represents 30 metres, and then we'll see 30 metres back in this section. So overall, the puck travels a total distance of 60 metres. Next, let's have a look at velocity, and the definition of velocity is the rate of change of position. So when we have a graph, the rate of change is a gradient. So when we're looking at a position time graph, it is the gradient of our graph that represents velocity. So in this plot, we see that the gradient is changing, showing us that the velocity of the puck is changing. Where the gradient is 0, we can say the velocity of the puck is 0. That is, we see 3 sections in the graph where the puck is stationary. Here we see a negative gradient. That shows us that the puck is travelling in the negative direction. Let's see if that makes sense. So we found Ada at plus 20. She'll be hitting the puck to the left, which is indeed the negative direction initially. Then we see that Ben hits the puck to Ada, and we see a positive gradient representing a positive velocity, or a velocity to the right in this scenario. So here, when the puck is travelling from Ada to Ben, we can calculate the velocity of the puck. We notice that the gradient in this section is constant, shown by the straight line. This means we have constant velocity from 1 to 4 seconds. Now the velocity is going to be the gradient of this section of our graph, which is just calculated by rise on run. So here we see that the rise is actually a fall in our line, meaning we have a negative rise of 30 metres divided by a run of 3 seconds. This gives us a velocity of -10 meters per second. Notice here, when Ben hits the puck back to Ada, represented in this section of the graph has a gradient in the opposite direction, a positive gradient, showing a different direction of the puck. Also, the size of the gradient is bigger. It's travelling the 30 meters here in a smaller period of time, in 2 seconds. So here, the puck is travelling faster because this straight line segment is steeper. So recapping, it's the gradient of a position time graph that gives us velocity. If we have a straight line segment in our graph, that means we have constant velocity. And it's the positive or the negative sign in our gradient that indicates the direction of travel. Now I chose this scenario with an ice puck travelling over ice because it's a very low friction scenario. So it is fairly reasonable to assume that as the puck is travelling, it travels with constant velocity. It won't lose any speed. However, if the surface changed to concrete, which is high friction, then we can think about, well, how would the motion of the puck change between these two time intervals? Let's assume the puck is still hit at the same time. Then in the high friction scenario, if it does get to Ben in the same position, it's going to take a longer time because the puck is going to slow down. So perhaps our puck won't make it until the 6 seconds. The question now is, how do we join up these two positions in our graph? A straight line is not reasonable here because this would indicate a constant speed or constant velocity, but we want to show the puck slowing down. To do this, we would have a steep line and then it would get shallower. Because remember, it's the gradient of our line that indicates velocity. So if the gradient gets less steep, as it does over here, that shows the puck slowing down. Here the gradient is nearly horizontal, indicating that the puck nearly stops at Ben. So initially we see the puck travelling its fastest because our line is the steepest. Then it's slowing down, the gradient's becoming less, until it's nearly coming to a stop. So it's important when we see a position time graph that you can interpret scenarios where an object might be slowing down or perhaps speeding up. Here, another way we can show that it's slowing down is that over the first second of the motion, it experiences a large change in position. However, over the last second of its motion, the change in position is very small, again showing that the puck has slowed down. So quickly recapping, a curved line in a position time graph means there's a changing gradient, which means there's a changing velocity, which we interpret as an acceleration.